Hey guys, so I thought I would talk through some of the physics of what's happening in a wire when current is flowing. Because if you think about it, it's more confusing than it seems, which maybe isn't encouraging, but it's not confusing in a very specific way, at least from my perspective. So if you think about all of the conceptual work we did earlier this year on electric fields and potential. What we got out of all of that is that if you have a potential difference between 2 points, that implies that there's an electric field acting between those 2 points. So if I start somewhere, if I have a point A here, or B, I guess I'll call it, and a point A here, and there's some VB here and VA, if VB is higher than VA, that implies that there's some electric field this way, assuming VB is greater than VA. In other words, there'd be some force that would push a positive charge from a higher potential to a lower potential. And that's part of the reason that we defined voltage, so we could talk about changes in potential as being a stand-in for how forces are working in this environment, or at least electric fields are working in this environment. So if you think about a wire, what we think should be happening is potential differences lead to forces, or more precisely to electric fields, which cause forces on charged particles. So what a circuit is you have a battery, and the battery creates a potential difference in a wire. So if I have point B over here, if that's point B and that's point A, then if I constrain my particles to move around in the wire, then I would expect a positive charge to move along the wire from point B to point A, which is what we see when we turn on a battery. We get a current that flows. We get current that flows this way, around from point B to point A. But what all of you found in the exploration is that that current is steady, and the current doesn't change no matter where you are in the circuit, unless you have a parallel circuit where there's potential branching of currents. But if you just have one wire running from point B to point A here, the current is steady and it's constant, which is sort of weird, because what I wrote here on the right is that potential differences lead to electric fields which cause forces on charged particles. So if current is a measure of how quickly charge is moving, and to an extent it is. So current is the rate of change of charge, or the rate of flow of charge. And you might expect that if charge feels a force in this circuit, that charge will accelerate. And if the charge is accelerating, shouldn't the current be increasing all the time? So this is the question that I have. If there's a force, why doesn't current increase all the time? I guess maybe over time is a better way to say that. This is an interesting question. So this is what I mean by things are a little bit more complicated than they seem. Because if you don't think about it that hard, sure, constant current flow, that seems fine. If you think about it a little bit harder, it seems like maybe current should be increasing over time because of an acceleration implied by an electric field, implied by a potential difference in the wire. So I want to talk a little bit about what's happening at a microscopic level to give you some intuition for why current does end up being steady in a wire. So let me scroll down here a little bit. So what if I draw a wire. And I'm going to do that. Aha, there we go. So this is a wire. Imagine this is a wire that extends. So the wire goes, wire continues this way, and the other way too. Wire continues, wire continues. So we're just looking at some section of the wire. And I've drawn an electron in the wire as that little black ball with an E- symbol. And I've given it a little bit of velocity down the wire. In reality, oh, and all these red things are atoms in the wire, because the wire isn't just empty space, it's made up of a bunch of atoms. And those atoms are probably organized in some sort of lattice structure. If this is a copper wire, which is pretty typical for the sorts of applications that we would be using if we were in the lab, and is typical for lots and lots of electrical infrastructure all over the place. We'd have a lattice of copper atoms, and there would be impurities in it. So you'd have different atoms mixed in with the copper atoms in the lattice, and the lattice would be vibrating. So you have a lattice of copper atoms that's vibrating, and you have electrons hopping from one valence band and one electron in one atom to another, and sort of being in between atoms from time to time. And the actual path that the electron would be taking would be very scattershot. It would be all over the place. It'd be ricocheting off of these atoms, getting propelled outwards in directions opposite it was just coming from after being absorbed and just scattered off. But I'm just drawing the electron moving down the axis of this wire, which, as you can see, if it were going to continue in that way, it would run into this atom right here probably and bounce off. This one right here, probably going to run into that one and then do something. But we can just kind of treat this as a one-dimensional problem to make it a little bit easier on ourselves, and know that this model really isn't that accurate, but it will capture some of the big picture things that will help us understand qualitatively what's happening here. So before, we had talked about what was happening to this electron is that it's being accelerated due to the potential difference of the battery. So we would expect it to accelerate based upon the electric field here. And as I've drawn it, I suppose if it's moving right, we'd expect a higher potential on the right side than on the left side. But so I guess we could draw that as there's some force from the electric field on the electron that goes that way. So that'll just be, Q times E, which I suppose would be minus E times the electric field here, which just from the picture that I drew points right. But this electron is going to run into a bunch of these atoms and start bouncing around. And the faster it moves, the more often it will bounce into atoms, and the more often it will be slowed down by those atoms. And so a reasonable model you might use for this is that there's some sort of drag force on the electron that's proportional to its velocity. So what if we work with that? So let's say that there's another force on the electron that goes this way. That's some sort of drag force. So that's proportional to that looks like minus BV, where B is some sort of drag constant. And we can think about what sort of quantities affect B, probably the density of the material for one. Certainly, if this were air drag, the size of the electron would matter. But maybe that's just proximity to other atoms here, which maybe is density again. So, but we're modeling some sort of drag. So the net force on our electron, if we're saying right is positive, let's say, that looks something like this. So there's some electric field and minus BV. Okay, so that's interesting. When we looked at air resistance earlier in the year, what you see if you have a net force like this is if you accelerate something and you have some drag force that's proportional to velocity, your velocity increases for a time and then reaches terminal velocity. And the terminal velocity would be when the drag force is equal to the force that's pulling your object along. So in the case of a parachuter, it's when gravity equals the drag force pushing back on the parachuter. In this case, it would be when the force from the battery supplied by the potential difference of the battery, that is the electron charge times the electric field, when that's equal to the drag force it's experiencing from hitting all these atoms all the time. So we should expect there's some sort of terminal velocity here when the net force equals 0. And that should be when this is true. If I make this one-dimensional, just to make it easier to think about, then that says when the force of the electric field that's being supplied by the battery is equal to this drag force, the magnitude of it, that's when I get terminal velocity. So, and this is predicting that we get some sort of constant velocity. So the prediction of this model is that velocity becomes constant. Velocity becomes constant after a short amount of time. And what I should be careful about here is this isn't exactly the electron velocity, it's how quickly the electron is drifting through the material, so that how quickly the electron is moving to the right here. Not necessarily how fast it's moving. The electron will still be bouncing around all over the place, so its actual velocity will be a lot faster than how quickly it can drift to the right. And if you want a more detailed description of that, I'd encourage you to look at section 25.8 of the book, which is pretty cool, and gets into some more of this. But the basic intuition that I'm trying to deliver here is that if you turn a battery on in a wire, no matter what's hooked up to that battery, if it's a resistor or wires or something like that, you should expect the current to be constant, to become constant very quickly because of all these frictional interactions between the charges that you're trying to move through the wire and the other stuff that's in the wire, the other atoms and impurities and stuff like that. So this prediction that velocity becomes constant also implies that current becomes constant too. Because if current is a measure of the rate of flow of charge, I'm going to write an equation down. So I is dq dt, the rate of flow of charge. And I can also write, and you can convince yourself of this if you think about it, that if I take the charge density, that is the charge per length in this wire, and multiply it by the velocity of the charges, I get the current. So if the velocity of the charge becomes constant, then the current flow also becomes constant. You can convince yourself of that and think about it. We can talk about it more, but I don't want to necessarily get into that here. The primary goal of this video is just to deliver a little bit of intuition about what's happening microscopically and how that influences the macroscopic behavior that we measure when we measure current. So I hope that was helpful. It's not necessarily super useful from a problem solving perspective, but I think it helps undergird some of the measurements we're making, and at least for me, helps explain something that I found confusing about current when I was learning about it. So I'll talk to you soon. Bye.